This lesson is on substitution and elimination, which may be familiar for Algebra 2 students, but then it extends the topic to an application with mixture problems. To review the steps for solving by substitution, you first want to identify a variable with a coefficient of 1 or negative 1, because when you solve for it, you won't have to handle fractions. And just to make sure we're all on the same page, why we just don't use the calculator all the time to find the intersection of two lines in a system, for example. When solving by graphing on a calculator, it might not be precise, especially when it comes to radicals. The calculator is going to give you a decimal approximation. So back to the steps for solving. After you find and isolate that variable with a coefficient of 1 or negative 1, you substitute its value into the other equation. What that does is fuse the two equations algebraically, mimicking that overlap nature of the graph. Always keep the visual in mind of what's going on behind the scenes with the algebra. Lastly, you substitute the result into any of the original equations of your system to find the value of the other variable and write your answer as an ordered pair. Looking around the first example, I spot a variable in one of the equations with a coefficient of 1 or negative 1, so I solve for it. Moving the 2y to the other side, I get x is equal to 4 minus 2y. From here, now that I know the value of the variable in one equation, if I'm to find a solution to the system, which means an ordered pair, an x and y value, that work simultaneously for each equations, then the value of x in the first equation, here, must also be true in the second equation, there. So I proceed by substituting in that value into the second equation. Replacing x with its value in the other equation. And solve for y. So those are the first two steps. For the third step, you take y's value and substitute it into either original equation, because it's going to be the same y for both equations, so then you're going to get the same x no matter which equation you substitute into. So you want to pick the one that's a little easier to work with. And right here, we won't run into any fractions since both of the coefficients of y are even. So I'll just substitute it into the first equation. This one is simpler because x is already by itself. So we find that the answer is the point of intersection 3, 1/2, and so that would make a consistent and independent system. It's consistent because there is at least one solution, and independent because the lines are with different slopes and they only intersect at one common point. Using substitution to solve the next example, I see that y is already isolated. So I substitute its value into the other equation, forcing that algebraic overlap that mimics the graph overlap. Substituting in gives the following. When I substitute in, I like to do so using parentheses, just in case there's anything on the outside to distribute. Combining like terms, okay, the parentheses aren't needed here, so this additive inverse pair, and I find that I have identity, and that means I have infinitely many solutions. So they happen to be the same line, and therefore they overlap entirely with one another on the graph. And therefore my classification is consistent and dependent. Again, consistent because there is at least one solution, there are infinitely many, and dependent because one line is dependent on the other since they are the same line. Now elimination takes a little more setup, and the main idea is you are going after additive inverses, because then when you add the two equations together, combining like terms, one of the variables will subtract out of the problem, leaving you with one equation and one variable, and whenever you have a match like that, you're able to solve the system. So if you had, let's say, 3 variables and 3 equations, you'd be able to solve it, or if you had 4 variables and 6 equations, you would be able to solve it. You have a couple extra equations in there, but as long as you have equal to or more equations than you have variables, you're in business. Back to the task at hand, you first want to identify a pair of like term variables. Choose the one with the lower least common multiple to simplify your arithmetic. Secondly, you want to multiply one or both equations to make the coefficients the same least common multiple. So the same. And then, if needed, change the signs of the term in one of the equations. So they are on opposite sides of 0 so that when you add them, they subtract out, and then you solve for the values of the variables, similar to the process of substitution. Jumping right into an example, I see that we already have a pair of additive inverses. So this is a nice warm-up problem where I will simply just add the equations together, combining like terms. And now I have 0y, so I won't write that. And I get x is equal to -2. Like substitution, I could take that x value and put it into either original equation. So it looks like the top one's a little easier. Solving for y gives a value of 5 for an ordered pair of -2, 5. And you could always check your answers by taking that ordered pair, like we learned in 3.1, substituting back into either equation in the original system, and ensuring that you have equality. So we presented our answer as an ordered pair, and then because there is only one solution, it is consistent and independent for the classification. For the next example, we don't have a set of additive inverses, so these were opposite in sign and the same distance from 0. So we have to figure out which one has the smaller least common multiple. The one for x, let's see here, between 4 and 6 is 12, and the least common multiple for y is, let's see here, 6 and 9, that would be 18. Well, because the one for x is lower, I'm going to create the additive inverse pair for x, because then I get to multiply by smaller numbers. Just want to simplify my arithmetic. So the top one I'll multiply by 3, and that will give me distribute to both sides, so all terms, in other words, get tripled. And then realizing that the coefficients of x have the same sign, they're both positive, I need to multiply the second equation not only by 2, but also by a negative. Might as well do that in one step. The less you have to write, the more you can focus on the pertinent details. Of course, you don't want to just skip steps if you think you might make a mistake. Always want to be careful and calculated when you skip steps. So now that I have a pair of additive inverses, I add the whole equation, each equation together. And please take note of the following. I multiplied by a -2. You will never see me just multiply by a +2 and then subtract the whole second equation, because then you have more work to do. You would have to realize that you are subtracting, or in effect distributing a negative, and then you have to add that. So really it's more work if you subtract the two equations rather than just add the negative, because that's the shortcut for subtraction anyway. So we add the system together, and we realize we had created two pairs of additive inverses on the left, and we find that 0 is equal to negative 54, not quite. So that would be contradiction, and therefore we say there's no solution, and this system is inconsistent. So these two lines never intersect, they must be parallel. Let's go ahead and do an application problem. These mixture problems will really test and expand your Algebra 1 skills of writing equations. It's a tough job, but I'm going to give you the really good strategies here that will take you through writing systems of equations from word problems. So let's see what we have. A vet needs 60 pounds of dog food that is 15% protein. He will combine a beef mix. Okay, that's the first time I heard a specific item, so I'm going to just label that X. As I read it, I give it an X, and I'm marking X clearly by writing that on the problem, and then I proceed, that is 18% protein, okay? With a bacon mix, okay, there's another variable, so I'm going to label that Y. If you wanted to say the beef mix was like, I don't know, F, and then bacon was B, you could do those things and flavor your variables in the context of the problem. Bacon mix is 9% protein. How many pounds of each does he need to make the 15% protein mix? Okay, we have two variables, so how many equations do we need? 2. So that's why this is a system type problem. So the first equation, let's see here, we have two things going on. The two big themes in the problem are percentage of protein and pounds of dog food. So if we handle pounds first, so that's one of the themes in this particular mixture problem. It might be something else in another problem. You just got to think about what the major ideas are. So pounds, this one is the trickier of the two equations because there's not much said about it, so you just kind of have to assume that, well, yeah, it's going to be X pounds of beef mix plus Y pounds of bacon mix is equal to, well, it says a total of 60 pounds. So whenever you're not given the specific information about how much of a quantity for your equation, then you could just assume that it's X for the one and Y for the other. The other big theme going on here is the percentage. So here you have to understand what's going on. This is hard in its own right because you need to take the fact that the beef mix is 18% protein. Okay, so then that means however many pounds X you have, only 18% of that mix is providing protein. So that as a decimal is going to be 0.18x. And then for the Y, the bacon mix only contributes 9% protein as a decimal, 0.09y. The next part is really important. The whole mix of 60 pounds is only to be 15% protein. So you will notice I will also multiply that 60 by a percentage. So product with a percentage and pounds, product of a percentage of protein with pounds, and product of the percentage with protein. Okay, so that's the theme for that equation. Do not forget on the right-hand side of this percent equation to take a percent of the pounds, because pounds was the theme for the first one, so that's just 60 pounds. But for this one, it's all about percentages. So you must have consistent parts to be in the same equation. From here, it looks like I could use substitution because I have x or y with coefficients of 1. You could put this into your graphing calculator and find the intersection of these two lines, but I'll here use substitution. So I rewrite the first equation so that I could solve for, I'll go for x. And then I will take that value in the second equation in replace of x, but I want to do something first. All these decimals, not going to work for me. So what I want to do is multiply this equation by 100 because they're percent decimals. And I will now get 18x plus 9y is equal to, now the product of 0.15 and 60 is 9, so then I get 900. Now I'll substitute in the x. Now I've created one variable equation, so I'll be able to solve for it. And again, this represents the overlap of these two equations, graphically speaking. And now I realize, 18 times 60, not looking forward to that either. So then I quickly look at all the numbers in the problem. But not all the numbers, but of every term, where this is like one term. And I realize that they are all divisible by 9. So I divide out that GCF, so I, in other words, distribute a 1/9 to every term, every product. So a 9th of 18 is 2. And there we are. No decimals, no large numbers, keeping the eye on the big picture at all times. Distribute that 2. And I find, well, let's see here, I labeled the y value as bacon mix. So that means I need 20 pounds bacon mix. Because this is a real-world problem, I don't just want to present the answer as some ambiguous ordered pair. So I want to say 20 pounds bacon mix, which contributes 9% protein. And then I need to substitute in x, so I might as well write here, because it's already isolated, rather than going back to any of the originals, because these two are equivalent anyway. So what I do next is substitute in the y value of 20 to find that I need 40 pounds of the beef mix. Make sure to label your answers. So does that make sense? Well, it needs to be 60 pounds, that's 15%. The beef is 18%, bacon is 9, and 18 is closer to 15. So I'm thinking I'm going to need more of the beef, and sure enough, I did.